Hello, my name is Jay Lim. Along with my advisor Santosh Nagarakate, we would like to show you an exciting technique to correctly approximate elementary functions for hundreds of representations and rounding modes. Everyone uses math libraries to approximate elementary functions, and it's paramount to approximate them accurately. In the RLIBM Project, we have been accurately approximating elementary functions by making a case for approximating the correctly rounded result of f of x and framing the problem of generating polynomial approximations into an LP problem. We were successful in generating elementary functions for the float type, but now everyone is designing their own representations and using different rounding modes for efficient hardware implementations, and we want to produce correct results for all of these representations and rounding modes, without creating 20 implementations for each elementary function. Instead, we propose a technique to produce a single polynomial approximation that produces correctly rounded results for all of these representations and rounding modes. The key insight is to generate a polynomial approximation for a 34-bit floating point representation with the round to odd rounding mode. Our mathematical proofs and experimental results show that such polynomial will produce correct results, and the resulting elementary functions are faster than mainstream math libraries. To begin, let me start by providing some background on correctly rounded results and our previous RLIBM technique. Consider these adjacent 32-bit float values. Most elementary functions cannot be exactly represented in float and need to be rounded to a float value using a rounding mode. This result, v2, is then called the correctly rounded result of e to the power of x1 in float with the chosen rounding mode. Through the RLIBM project, we have been making a case for generating polynomials that approximate these correctly rounded results. The intuition is that there is a range of values near the correctly rounded result where all values in the interval round to the correctly rounded results. And these intervals define linear constraints for the polynomial approximation we wish to generate. So we encode these constraints into a system of linear inequality and use linear programming solver to generate a polynomial that satisfies all constraints. This polynomial guarantees to produce correctly rounded result of f of x for one chosen representation in rounding mode. But now our question is, how do we generate a single polynomial that produces the correctly rounded results for multiple floating point representations? A naive way of doing this would be to use an existing math library. For example, let's say you have a correctly rounded math library for the 64-bit double representation, and you want to produce correct results for float. Naively, we can take the float input, convert it to double, use the double math library, and round the double result back down to float. But then this result can be wrong. Why? It's because of double rounding. When we round a real value of f of x to double and then subsequently round this result again to float, it is possible to produce wrong result because rounding twice can result in a change in the rounding direction. But RLIBM all is all about avoiding this double rounding error. In RLIBM all, if we want to generate a single polynomial that produces correct results for 10 to 32-bit floating point representation, then we generate a polynomial for the 34-bit floating point representation using a rounding mode known as the round to odd mode. How does this rounding mode work? If the real value is exactly representable in our representation, then we represent it with that value. Otherwise, we round a real value to an adjacent value where the bit representation is odd when interpreted as an integer. And the amazing thing, which we formally proved in our paper, is that this round to odd result is guaranteed to produce a correctly rounded result when the output is rounded to any 10 to 32-bit floating point representation with any standard rounding mode. Using this technique, we created several elementary functions that produce correctly rounded results for any floating point representation from 10 to 32 bits, with all 5 IEEE 754 standard rounding modes. And not only that, our experiments show that RLIBM all is faster than mainstream math libraries. Please see the paper for more details about our experimental results. In conclusion, let's say you want to generate a generic math library that produces correctly rounded results for all representations up to n bits. Then you would generate a single polynomial approximation for the n plus 2-bit representation using the round to odd rounding mode. Our resulting math library produces correctly rounded results for hundreds of floating point representations and rounding modes, and is faster than mainstream math libraries. There are a lot of details that I couldn't cover in this talk. Please see our paper for proofs, algorithms, and experimental results. Thank you very much. We're continuing to improve our elementary functions. Please give RLIBM all a try.